Hello coders, I welcome you all. In this video, we are going to implement RAG, Retrieval Augmented Generation from scratch, step by step. So before we jump into the practical part, first let's understand what problem RAG is trying to solve. Think of a hospital. Every day, doctors and staff create many records like lab reports, prescriptions, patient details, and so on. After some years, this becomes thousands of PDF files stored in the system, right? Now, if doctor asks, can you show me the recent lab results for patient ID 245? This looks simple, right? But in reality, searching hundreds of files by hand is very slow. If you ask a normal AI, means LLM, like ChatGPT, it cannot help. Why? Because it doesn't know about your hospital's private data. It only knows general medical facts from the internet, right? This is common problem of each and every LLMs. You might think, okay, then let's just upload all these files to the LLM. But the problem is that's not really possible. Here is why. Every LLM has something called a context window. Think of context window like a box. It can only fit a limited amount of text at a time. Thousands of records simply will not fit in LLM because of context window size, which is limited for every LLMs. Even if you somehow pushed everything inside, it would be very slow and very expensive to do this again and again, right? So now the big question is, what would the ideal system look like? The ideal system should be smart. It should search only the documents that matter for the question. From the large amounts of documents, it pick out the exact pieces of text that are useful. It send just those pieces to the LLM and then let the LLM generate the final answer in a clear way. And this is exactly what RAG, or Retrieval Augmented Generation, does. Don't you worry, we are going to implement all the steps from scratch, step by step. Just listen this carefully. You can consider RAG like giving the LLM a smart assistant, one that quickly finds the right files and then lets the AI, means LLM, explain them in a simple language. Alright, now that we know why we need RAG, let's understand how it actually works step by step. Think of it like this. RAG has two main parts, retrieval and generation. So now this is our step number 1. So first we take all the documents like PDFs, reports, notes and break them into smaller pieces of text. Why? Because AI, means LLM, understands better when the text is in small clear chunks instead of huge paragraphs. It's like cutting a big cake into slices, which much easier to serve and eat. Hope all of you are clear with this, right? This is step number 1, break the data into chunks. So now let's move to our step number 2, create embeddings. Next, we convert each chunk of text into numbers. These numbers are called embeddings. They capture the meaning of the text. For example, if one chunk talks about blood test and another talks about lab reports, their embeddings will be very close because they mean similar things, right? So now in the second step, we will create embeddings. Now in the step number 3, we will store embeddings in a database. So all these embeddings are stored in a special database called a vector database or vector store. This database is like a smart library that doesn't just match words, it matches meanings, right? So this is our step number 3. We will store embeddings in a database inside vector database or vector store. Let's move to our step number 4, retrieve relevant chunks. Now when a doctor asks, this is our query, can you show me the recent lab results for patient ID 245? So here user, means doctor, asks this particular query, right? So RAG will take this question and turn into an embedding, then search the database for the closest matching chunks. So instead of reading all the files, it quickly finds just the right pieces, right? Because we have already converted our reports, PDF, etc. into embeddings. When we receive this query, we are also converting this query into embeddings. and then search the database, means our vector store, for the closest matching chunks. So instead of reading all the files, it quickly finds just the right pieces. Now let's move to our step number 5. We will send it to the LLM. Those relevant chunks are then passed to the LLM. In our case, Google Gemini, because we are going to use Google Gemini. Now Gemini has the context it needs, right? Context we got from vector store. It knows both query and context. Hence, the doctor's question as a query and the exact patient records related to that question from the vector store, right? So now let's move to our step number 6. Generate the final answer. Finally, Gemini, means LLM, uses its language skills to generate a clear and human-like answer. Something like this. Patient ID 245 had lab test on January 5th, March 12th, and June 20th. And the results were this. With source information. Hope all of you are clear with this, right? And that's the magic of RAG, Retrieval Augmented Generation. It's not about making the LLM memorize everything. It's about teaching it how to find the right information at the right time. Now let's summarize entire RAG process. First, user asks a question. Let's say, what is the vacation policy? Now, instead of directly sending this question to Gemini or any other large language model, we take a smarter route. We first send the query asked by the user to an embedding model. This model doesn't just keep the text. It converts the question into a vector, which is a basically mathematical representation of the meaning behind the sentence. At this point, now we have two things. First, the original query in plain text and its vector form, which captures the deeper meaning of the query. Now, here is the important part. Let's assume that earlier we have already taken all our documents like HR policies, PDF files, or internal manuals and converted each of them into vectors in the similar way. Means similar way as we have followed for user question. Now all of our vectorized documents are stored in what we call a vector store. So this is our vector store. Now just imagine we have a big collection of documents, each represented by a vector that reflects its meaning. Now comes the key step. We compare the user's query vector with all the document vectors in my vector store. This comparison is done using a method called cosine similarity. Think of it like measuring how close two arrows are pointing in space. Now, whichever document vector is closest to the query vector, that's likely the document that matches the user's intent. So we pull out the matching document, but please remember, we don't need its vector anymore. I need the original text of the document. Now I take the user's original question and add this relevant document text as context that we have fetched to vector store and converted back vector to text and fetch relevant document from here, from our documents. Hope all of you are clear with this, right? So I'm repeating, we pull out the matching document, but as I said, we don't need its vector anymore. We need the original text of the document. Now we take the user's original question and add this relevant document text as context. After that, we are sending both user's question and his context to LLM, and LLM will generate answer based on this context. No any guesses, right? Because we have already provided context with user's query. Means we have provided question with background information. Now, when LLM answers the question, it's not just guessing based on general knowledge. It's giving a response based on real relevant documents from inside the company. That's the core idea of RAG, Retrieval Augmented Generation. It helps model give grounded, trustworthy answers, especially when you want it to work with your private data, not just public internet data. Hope all of you are clear with reg. If you don't fully understand some parts on the first watch, I recommend watching it one more time. And I'm sure by the end, you will have a very clear understanding of reg. So this is all about our theory part. Now let's move to the practical part. Let's jump to Jupyter Notebook. So now let's start with step number 1, where we are going to prepare some sample documents. So we will start small and keep things simple, right? So as you can see, I have created 4 short patient reports using Python dictionary. You can see patient 1, patient 2, patient 3, and patient 4. 4 short patient reports. So later in the future, we can scale this to a real hospital data like PDF, lab reports, prescriptions, or even x-rays as well. But for now, let's just use these small examples to understand the process, how reg works, right? So you can see here are our 4 reports. Patient 245 had a blood test on this date, right? Patient 312 came for a follow-up on this particular date. Patient 411 had an X-ray on 5th September 2023. Patient 587 had a follow-up on 15th November 2023, right? So each report has a title that you can see and a short text description and key details like test results that you can see. Hemoglobin levels, cholesterol levels, scale showed blood sugar levels likewise. So this is the sample data we will use to start building our reg system, right? Let's execute this cell. Done. So this is our step number 1. We have prepared some sample documents, means our 4 patient reports. Let's move to our step number 2. Paste the import and API key. Let's create some more cells. So now we are going to test if the library is installed properly or not. Also whether our API that I have created from Google Console for Gemini. So we are going to check whether our API is working properly or not. If it runs without an error, it means everything is set up correctly, right? So first, let's import OS. Then we have to import Google.GenerativeAI as Gen AI. Also to load our environment variables, we have to import from .env import load underscore .env. Let's execute this cell. Done. Now let's load our environment variables load underscore .env. Done. Now let's configure our API. So in my case, my API for Gemini is already available in .env file. So API underscore key os.environ, and here I have saved my API key with this particular name inside .env file Google underscore API underscore key. Let's execute this. Done. So now our API connection is working. Now let's check which models are available in Google's generative AI. So we can do this using the list underscore models function. This function will return a list of all models that we can use, like chat models, text generation models, and embedding models. Let's check. So for that, we have to write for model in GenAI dot list underscore models, and let's print model. Let's execute this cell. I think we have to wait. It will take some time. And you can see list of models. You can see like chat models, text generation models, and embedding models. But we are interested in embedding models. Let's move down. So you can see text underscore embedding 4. So let's use this model. Let's copy this name and let's paste it over here, right? So because this model is designed to convert text into embeddings, means the numerical form that captures meanings, right? So for that, we are going to use this. There are many, but we are going to use this one, right? So now let's move on. So now here is our next step. Step 4. We are going to create an embedding for a patient data, just for one patient data, right? Now that we know which embedding model to use, this one, right? So let's actually try it on one of our patient reports. Let's try on this patient report 245. Let's move down. So what we are going to do, we will take the text from patient report 245, this one. After that, we will send it to the embedding model that just we have selected, this one. And this model will return a vector, a list of numbers that capture the meaning of this text called embeddings, right? Let's do this. Again, let's move down. So we have to write GenAI dot embed underscore context. Here we have to use embedding model that we have selected. Let's copy this. Let's paste it over here. Also, we have to provide context patient underscore 245, and we are interested in text, and task underscore type is equal to retrieval underscore document. So please look at here what's happening in this code. We take a report text for patient 245. Now we call the embedding model, this one, text hyphen embedding hyphen 004. So here the model returns a vector of numbers. This vector represents the meaning of the patient's report. Let's execute this cell. Sorry, here is a spelling mistake. Retrieval, retrieval underscore document. Let's execute it one more time. Done. You can see embeddings for this particular patient ID, right? Let's assign it to one variable, patient underscore EMB. Let's execute this one more time. Then let's print this. You can see. So this vector represents the meaning of the patient's report that you can see. And you can see long list of numbers. This list is called the embedding vector, like the fingerprint of the text. Please remember this, right? So now let's check how many numbers are there inside this embedding vector using this length function. So here I think we have to print only embedding, and you can see 768. It means the report is represented by 768 numbers, 768 dimensions. So each number captures a small part of the meaning, and together they represent the whole report using this many numbers, right? Using embeddings. So this is our step number 4. We have successfully created embedding for a patient data, for a single patient data. Let's create similar for our next patient as well. One in patient this. Let's take 312. Let's execute this cell. Done. Let's check similar vector having similar length as well, 768 dimension, right? So you can see now our both reports are converted into numbers that capture their meaning, right? This is for patient number 1 with patient ID 245. You can see embeddings, and this is for patient number 2 having patient ID 312, right? So both reports are converted into numbers that capture their meaning. So instead of writing the embedding code again and again for each patient, let's make a small helper function. This way we just call the function whenever we want to create an embedding, right? So now let's create our helper function with name embed text. You can give any other name as well, and it is taking text, and this function will return embedding. So again, let's copy this that we have already created, and let's paste it over here. Just we have to remove this, and let's make it proper, and this function will return embedding, right? Exactly this code. Just we are putting this code inside function, nothing else, right? And we are returning embedding. Let's execute this cell. Done. So now instead of writing the same code again and again, we can just call this particular function embed text whenever we need an embedding. So now our embedding function is ready, that will return embedding. So now let's store all patient reports in a data frame, in pandas data frame. So this will keep everything clean and easy to work with. So for that, first let's import pandas as PD. Now here I am creating one list. This list contains every patient documents, in our case Python dictionary, that we have created at the beginning, right? All for patient reports. Let's move down and let's create pandas data frame with this all documents, and let's assign it to df. Let's execute this cell. Let's check. Done. So we have title and text. I think let's rename this columns with id for title and text for text. Let's execute this cell. Let's check one more time. Done. id and text. Now it looks better, right? So what we have done here, we put all patient reports into one Python list. Then we convert that list into a data frame, basically a table. And just we rename the columns so it's clear. One for the patient ID and one for the report text, right? So here is ID and text. Done. Now in the next step, we are going to add embedding over here for this reports, every reports, right? So we will create one new column over here for embeddings. For that, just we have to take this text, this, and just we have to apply our created function embed text, this one, right? That just we have created. It will return embedding. And let's create new column with name embeddings here in our pandas data frame. Let's execute this cell. Done. Let's check. Great. You can see ID, text, and embeddings. So again, let's revise what's happening. Pandas goes through each row. Each row in our text column, each patient report. For every report, it calls our function embed text function that we are calling from here using apply, right? So for every report, it calls this particular function to generate embeddings. So this function generates embedding vectors, a long list of numbers, right? Finally, we are storing these embeddings into a new column with name embeddings. Done. So now our data frame has three parts: ID, text, and embeddings. This is the foundation of RAG, Retrieval Augmented Generation. From here, we will be able to compare embeddings and find which patient reports are most relevant when a doctor asks a question, because now we have embeddings for each and every reports. As you can see, this is very simple table, and this is a vector store, our vector database, right? That just we have created from scratch. Then as I said, this is the foundation of RAG, Retrieval Augmented Generation. Now let's move on. So now as you can see, for each and every reports, we have embeddings. Suppose a doctor asks a query. Show me the blood test details for patient ID 245. So now we have to convert this query into embeddings, right? After that, we have to find similarity. So for that, we are going to use cosine similarity for this comparison with query with this embeddings for reports. So let's create function for this. So for that, we have to import numpy as np. And let's create one function, query underscore similarity underscore score. And input is query asked by the user and vector, this vector. And for user query, also we have to convert that query into numbers, means embedding. So we are calling this function for user query to convert this query into numbers, into embedding vectors, this function, right? It returns embedding for our query, which is asked by the user. Assign it query underscore emb is equal to this statement. After that, let's find cosine similarity. Also, we can use dot product, which works since embeddings are normalized. So dot query underscore emb, which is embedding vectors for query and vector, these vectors from our vector store. Let's convert it into float and let's return this score, cosine similarity score. So let's revise. So this function takes a query, user query, asked by the user, in our case, doctor. It turns it into embeddings, then compare it with a patient report embedding and returns a similarity score. Cosine similarity score means if the score is high, it means the report is very relevant to the query. This is how our system knows which reports matter most for a doctor's question, right? So now let's create a user query. In our case, this query will be generated by doctor query, which is something like this. Can you show me the recent lab results for patient ID 245? This is user query asked by user. In our case, doctor, right? Now after that, we have to take this column, embeddings, that just we have created. Embeddings for each and every reports. And here we have to use apply. And I'm using lambda function, vector, each and every vectors, and we are calling query underscore similarity, this function. Let's copy and paste it over here. And here we want to find similarity between query, this one, and all the vectors available inside our vector store. Let's execute this cell. Oh, LMBDA. Sorry for this. Let's execute this cell one more time. Name error, name query underscore similarity underscore score is not defined. Oh, sorry. Because I haven't executed this, and this. Done. Sorry for this. I think there is some problem. Let me check. You can see embeddings are same. So that's why similarity scores are also same. I think I have done some mistake. Let's check this function. Embedding. Oh, this is just for one patient. But we need for all the patient reports. Let's remove this. Now done. Let's execute all the cells. Sorry for this. I think done. Let's execute this all. Now we have proper similarity score. This is our cosine similarity scores. Let's create new column in our data frame. Actually in our vector store with name similarity. Let's execute this cell. Let's check. You can see here. Now we have patient ID, text means reports, and embeddings for each and every reports, and similarity score. So now we have similarity score. Now let's sort this data frame by similarity score, and we want highest score at the top. Sort underscore values by this cosine similarity score, and we have to make ascending to false. We want in descending order, highest similarity at the top. Df new is equal to this. Let's execute this cell. Let's check. You can see highest score at the top. Now to find most similar document, let's create one helper function. Means we are going to combine all these steps that we have done earlier. Def most similar underscore doc. It is taking query, and let's copy this. It will find similarity score. Also we are sorting these values, and from this we are taking ID from the sorted text top underscore ID, right? We are interested in ID because it contains source information. Let's copy this. Let's paste it over here. Top underscore text for this top similarity score, cosine similarity score. We are taking this particular text and this particular ID over here. Let's return top underscore ID and top underscore text. So what this function is doing, it is taking doctor's query, compares it with all patient report embeddings, then it sorts the report by similarity score. Finally, it picks up the top result, the most relevant report, and also ID, and it is returning it, right? Let's execute this cell. Done. Now let's build the full reg function. Let's define reg, which take user query as input, and it will call this function which returns top ID and top text, source information, and top matching report. Here we have to pass query. Now very important step, GenAI and generative model. Here we have to give one model. Let's try Gemini underscore 2.0 Flash. This is LLM model, and let's assign it to one variable model. Now let's build one prompt and I'm going to use f string. Answer this query, and here I am passing query asked by the user, and only use this context to answer. Which one? Top underscore text, which will be written by this, which is top matching here. So we are using this as a context for the query because of top matching. Then model will generate content from this prompt and we are storing it as a response. Let's first print response. Let's execute this cell. Done. So again, let's use this query. Now let's call our function with this query and let's print this output. Let's execute this cell. Oh, nice. You can see it is printing this text as an output. Let's print it in proper format. Let's create proper response. So I am building nice response. Source title, I want to return source as well. Patient report ID, and here top underscore ID. With response, I want to return source information as well. Again, use f string in return and response dot text only. We are interested in this text only. And in new line, source document is source underscore title. This one. Let's execute this cell, this and this as well. Oh, nice. You can see patient ID 245 had a hemoglobin level this, and this is the output. And the base is source document is this. Now we can say our RAG is working properly. Now let's ask another query. Let's copy this. Let's paste it over here. Patient ID 312. And what is the latest cholesterol level for patient ID 312? Call this with this query. Oh, great. You can see the output. Now our RAG is working properly. You can see the model answers using the written document, which is our context. So having the highest similarity will become our context for our query. Hope all of you are clear with this, right? How RAG is working. So I am repeating, the model answers using only the retrieved document from our vector store. And we also saw which report was used as the source. This way RAG works. Hope all of you are clear with this, right? How RAG is working. So let's revise it once. Big models don't know your private data, right? You can't dump all your files at once. RAG solves this like search first, then ask. In the step 1, we have to find the right document using cosine similarity, right? And give that document to the LLM as context along with the query. Get the answer with the source. That's all about RAG. I am sure you are clear with retrieval augmented generation RAG. I hope you like this video. Please don't forget to subscribe this channel. If you like this video, smash that like button. Thank you very much for watching this video. Take care. Bye-bye. See you in the next video.